So this is a problem we went over as we started to transition from doing horizontally launched projectiles into projectiles that are thrown at an angle. And they're basically the same problem. We still use a constant velocity situation for horizontal and a constant acceleration situation for vertical. But we just have to make sure we're organized in how we draw pictures and set our tables up. So let's draw our two players here. And there's our picture. Basically, in this picture, we're going to be looking at distances. And what makes this problem a little bit simpler than it could be is that we say that one of the players catches it at the same height the other player throws it from. So that means that we can sort of set any origin we want, but y and yo are going to be the same height. So I think the easiest origin to pick is to call the launch point 0, 0. In that case, whatever final distance she's standing at is x comma 0. So we'll use this picture to figure out distances in meters as we fill out our table. How do we handle the angle of 34 degrees? Well, actually in an entirely different picture. So I'm going to write my 11 meters per second. I'm going to write my 34 degrees. And we're going to use this picture to break that 11 meters per second into a VOX. How fast is it moving along the ground? And VOY. How fast is it moving up and down as we start? This picture is going to tell us about velocities. It's important to recognize that this exists in real life. This is what the ball's path is going to look like. This is just a formalism we're using. We're using the triangle geometry to break the real velocity vector, the 11, into two components. You can't mix these two pictures for a couple different reasons. If you ever find yourself doing something like this, and many students will try it at some point, oh, well, I can figure out distance by just making this into a triangle, and we'll call this half of the total distance, and we'll call that 11, and that's 34 degrees. You've got really two big issues here. The first is that this would be in meters, and that's in meters per second. And you're mixing two totally different concepts that aren't that related to each other. So if you ever find yourself putting one unit on one part of a triangle and one unit on another part of a triangle, that's kind of a big alarm bell. There's another even more fundamental problem here, though, which is that trigonometry, triangles, involves using triangles. And this is not a triangle. This is a pizza shape. See, I even drew some pepperonis for you. So you cannot do any sort of trig with an arc like that, with a curve. So if you ever find yourself just trying to do this with no physics, just drawing a picture and doing opposite over hypotenuse on a random shape, that's a guarantee to be wrong. So just be careful there. Of course, the way we combine the information from our two pictures is to make a table and to use equations. So let's do that. Here's my horizontal. Here's my vertical. And we can have the same information in each dimension. And when we start to fill this out, of course, we know the accelerations for anything influenced just by gravity on Earth. Those are our accelerations. VOX and VOY we're going to find from this triangle. And the distances we can read off this table. XO is 0, X is unknown, YO is 0, Y is unknown. Or excuse me, Y is 0 as well. All right, so let's figure out VOX and VOY. Basically, we're just going to have to do sine and cosine. So sine of 34 degrees, cosine of 34 degrees. Opposite over hypotenuse. This one's going to get me VOY. This one's going to get me VOX. So just do a little bit of trig. So we've got 34 sine times 11. This is going to be 6.15. And this one is going to be 34 cos times 11. That's going to be 9.12. So now we can go back and fill out our table. VOX is, this is actually tricky. Make sure you put the right one in the right place. VOX is 9.12. VOY is 6.15. All right, almost done. The last thing you need to do is you need to do an equation for X and an equation for Y, like we would in any projectile problem. All right, so we're stuck there. So now it's time to do our vertical. So the fact that these are both 0 for our positions is really nice because we're starting to fill into what looks a lot like a quadratic equation. It's got a t and a t squared in it. And were either of them not 0, we would in fact have to use the quadratic equation. But since they're both 0, the equation simplifies to this. And since there's a t in every term, or the term is 0, we can just divide through by t. And we get a lot of canceling, which is sweet. So if we add 4.9t to both sides, we get 4.9t equals 6.15. So I ran out of space due to poor planning, but if I just divide both sides by 4.9, sorry about my poor planning. All right, 6.15 divided by 4.9. I get t is equal to 1.26 seconds. So now that can just be plugged in over here. So the distance the softball player is standing is 1.45 meters, or 11.45 meters. So that's pretty much it. We'll basically practice this many times, but at the end of the day, we still have picture, table, and one equation for each dimension. The only thing new is any non-zero velocities, we draw a hypotenuse with that velocity. We break into components using sine and cosine, and then we proceed.